Ingo is the Chief Technology Officer for Spaceflux. Okay, I'm not going to tell you what Spaceflux is about because this is the subject of your talk. Okay, no spoilers. Prior to this, Professor Waldmann's career brought him into the exciting worlds of astrophysics and artificial intelligence. Okay, where he was a professor at UCL and a fellow at the Alan Turing Institute. So the title of your presentation is Enhancing Space Safety through Global Optical Space Domain Awareness. Sorry.
Thank you very much, and thanks for the invitation. So, yeah, I'm Ingo. Hello. 1, 2, check. Okay, well, thanks very much, and thanks for the invitation. I'm Ingo, and thanks for the introduction. So who's Spaceflux? So we are a young UK-grown startup. We're now 3.5 years old. We've just opened our first international office, which is in downtown Venice, which is quite nice. So if you ever want a business trip to Venice, come talk to me. That's our team, the team building at the moment, and we are an optical SSA and SDA company, and we have a very strong partner now with the UK government, who have been our anchoring partner, which is very nice of them. But what do we do, and what the problem is? And I'm preaching into the choir here. Everyone knows what the actual issue is. It's orbits are getting quite crowded now, especially the lower orbits. We have a lot of debris going around, but it's the active satellites that are increasing rapidly in number. And it was about 4 years ago when we decided to let's do a little bit of a spin out and try address some of this monitoring need that will come up in this domain. And space situational awareness and space domain awareness, was a thing 10 years ago, but it was quite a marginal and niche domain. Now, if you try to get into the Amos conference, you have to pre-book months in advance, otherwise it's booked out. Before that, there were 50, 60 people there. And the reason is the large, proliferation of active satellites, and with that, the amount of debris that is a danger to the satellites. So that obviously impairs our ability to operate across all domains. And that's not only LEO, but increasingly GEO is also extremely overcrowded at this point, with some debris flying around. And it also, when we started the company, the threat assessment was slightly different. It was more the 5-centimeter fast-moving targets. Now there's a whole geopolitical threat to space safety that we need to address, which we've been coming into. So how do we do it as a company? We have built a global network of optical sensors. I mean, I'm an astronomer, I call them telescopes, but in this domain, it's a sensor. And we have different varieties of them, looking at different orbital regimes. So I've been warned about this. Ooh. Okay, there. We have the mastery of the pointer. We have wide-angle lens arrays that look a bit like Wall-E, that we are rolling out across the world. This is our Western Australia site. The next one's going up in New Mexico. We have Spain, and we're rolling out 8 more. Looking at the LEO domain, basically finding everything that runs around in LEO and cataloging it and keeping an active catalog of the satellites, and that really helps you to prevent collisions, but also understand changes in behavior, and also your atmospheric upper density models can be inferred from that. Then we have our standard model, which is the far left here. I'm not trying to point on it. Is our normal small telescopes that are very fast steerable, and we're moving to meter-sized telescopes now for daytime tracking of satellites in the infrared, because one of the problems with optical is the sun quite often. Now, we have a very strong partnership with the UK, and we're very proud to have a very strong partnership and very thankful and fortunate. And we provide multiple services to the UK. So one starts with sensors. So we provided the first sovereign SSA capability at the UK Cyprus base for the UK Space Agency and UK MOD. We provide all of the optical data now for all of the Panoptis programs, ranging from LEO to Cislunar. So lot 1 to lot 3 is all of us. So we really fear Christmas and the Christmas break and hope that nothing goes wrong. But it's across multiple agencies, and especially, we've already heard about NSPOC being a very, very good joining of forces between the UK Space Agency and the Space Command. And we talk to them daily, and it really works. It's really nice to see, actually. And we provide software, data analytics software, the data pipeline software into Borealis, for example, through Panoptis, is something we provide as well to the UK. Now, I just wanted to show you a few fun sort of case studies. Not quite Vera Rubin style level of awesomeness, but it's you can't really beat that. So I'll try, but our data isn't quite as pretty and sexy. But what we do provide is near Earth meteorite detection, and anything that flies through any interstellar visitor, we will see and provide that to the UK Space Agency as part of the Planetary Defence Initiative. On the right-hand side, this was an Intelsat breakup last year, which Intelsat had just a big explosion, and we were the first ones to report in the world on the debris field, and then track the debris field as it made its way around the geo belt over the next coming days. So that is obviously very important if you want to, keep your very expensive geo assets safe and maneuver away from that. So it's detecting new stuff, but it's also detecting new behaviors, which is very important to keep things safe. And this is a perfect example, quite a classic example. It's Cosmos 2553. If you know what that satellite is, you know. If not, Google it. I'm not going to go into it. It's not something you want to see out of control. It's been orbiting inside the Van Allen belt, and around the 23rd of April, it started spinning uncontrollably with a period of 2.18 seconds. So this is a very, very large satellite that spins extremely quickly. And you can see this is the data from our Cyprus sensor site. So not Nix Alpha, but we have one next to the UK base, because why not? And you can see that there are two frequencies here, one and the other one, and they're not harmonics of each other. They're actually two separate spin angles that happen simultaneously. So there's a two-axial spin to this. So if you then look at the power spectrum, and this is slightly technical, but please bear with me, you can see the behavior change down here, and you can see these two frequencies down here, and you can see there's a slight slant to them. So the satellite is starting to slow down in its spin, but this is not something that an operator has managed, but this is entirely consistent with momentum transfer and with solar radiation pressure. So they've completely lost control over that, which would suggest that there was a power surge in the control module that led to this misfiring and then the complete lack of intervention later on. It being in the Van Allen belt and being in a very high charge environment makes a lot of sense. But you can start by using optical data, because you have the photometry. You can start inferring what went wrong and whether it's savable or not. Now, I've already said the daytime is a bit of an issue if you have an optical telescope network, but we've been fighting it, and this is our first daytime site. It's in Spain. It's in southern Spain. It's a 70 centimeter telescope in the infrared and optical, going from 0.4 to 1.7 micron. And this is we've taken this last Tuesday a picture of the International Space Station during midday, during lunchtime in Spain, which is quite nice. So there's going to be a docking event relatively soon, a Dragon module, and we're going to monitor that as well. That was in collaboration with DSTL, because they're quite interested in understanding what satellites are doing when the sun is behind them, and it makes it usually, traditionally quite hard to see intent during those times. And the infrared sensor really, really helps. It's been a long project because trying to make this fireproof is really hard. There's a 70 centimeter lens that you're pointing really close to the sun. There had to be a lot of stuff going into that not to burn down the observatory. But we finally got there, and this is something that we will provide commercially in Q1 next year. Another fun thing that we've been tasked and stuff that we do for commercial customers is checking the health of constellations and the health of satellites and deployments generally. And this is a fun one where a VC of a company that's been launching a fleet of satellites had the impression that the board was lying to them about the health of their deployments and contacted us whether we can find out whether they actually deployed properly. Turned out that the board was lying to them, but they have quarterly board meetings. By the next board, they had sorted out their stuff. They had to retract and expand their solar arrays a couple of times to make it work, but finally it did, and it's been healthy ever since. But this is another aspect of what we're trying to provide for the UK community as well, and internationally more generally, is health monitoring of their assets, regardless of whether it's in LEO or in GEO or anywhere in between. Because this is what you can do with optical very well. And we've heard the radar talk, and I do really want to talk to those guys, because that is just complementary to what we do. And it's this larger infrastructure that we're building in the UK, radar and optical, that really, really allows us to understand what's going on up there. This is something we've trialed as a pilot, a phase 1 and phase 2 studies, and a phase 3 is coming, hopefully, with Space Command. And it's predicting behavior of geostationary satellites and giving people warning of when something comes very close to their assets, in this case, Skynet, for example. And that happens on a regular basis. And what then the operators really need and really want is as much data as possible to make informed decisions. And we predict these events forward, and then we task our network automatically, agentically, to provide as much information as possible. By the way, that's just a graphic down there of the Intelsat propagating across the globe from earlier. Right, and I think, not to bore you too long, I'm going to wrap it up quickly. I'm, an astronomer by training, and I'm still at UCL. They've just lent me out. They've rented me to the company, and I find that the real way of innovating this domain is a very young domain, and it's very fast growing with very many low-hanging fruit, but it is a big data problem. There's so many objects now, there's so much data. One of our optical lens arrays, the wide angle ones, provides 2 terabytes a second in data throughput. We have many of them, so we have hundreds of terabytes a night sometimes that we need to process. So this is perfect for machine learning, right? And this is something where academia can really help, and we're trying to build these academic relationships with loads of institutes in the UK and more broadly by providing data. So this is something that we'll make available to academia, because we have quite a lot of that, and run machine learning challenges in a larger domain. Because we do think that collaborating with academia is the way we can solve this in a really creative manner. And for that, we're actually starting to sponsor internship students now, but also PhD students, to actually try to work out whether we can calibrate upper atmospheric models with satellite data. So we have enormous amounts of satellite passes, especially in the lower LEO regime. And by just measuring the delays every time they come around and hit our sensors, we can actually start providing interesting data that is useful for the Met Office and others to calibrate upper atmospheric drag coefficient models and make drag re-entry modeling so much more precise and easy. What we want to really focus on is to provide real-time drag data to the space community. Now, that's basically all, because I've run out of time, but I also ran out of slides, so thank you very much.
Thank you very much, very insightful. Any questions? Yes, over there, please.
Thank you very much, very interesting indeed. If you find an interesting astronomical object or event, how do you communicate that to the community? Because presumably your customers are normally not the astronomical community.
We post it on the appropriate forum as much as we can. So we do get tasked quite often, but finding, measuring some meteorite or something. So that happens relatively frequently. And I've got my astronomy mates at different universities. We get the message out, but we are also very happy to just receive feedback and receive, if someone wants us to look at something, we're very much up for that as well. So it's we want to provide that service also for the astronomers as much as we can.
Okay, more questions in the room or online? Yeah, okay, go ahead.
Can you give any detail on the fireproofing?
No, sorry, the fireproofing. Don't point at the sun. So we have multiple sun avoidance systems in there now. Photo sensors, emergency shutters, cooling systems that kick in. One of our competitors, I'm not going to name now, have a similar daytime system, and they was like, look, we are competitors, but please put as many systems in as possible. Apparently they had their entire CCD camera melt at some stage. But it's not only that, it's the computing power, the uninterruptible power supply in a Spanish summer gets up to 50 degrees quite quickly, so you have to monitor everything. We have an enormous number of temperature sensors and emergency shutdown procedures. So far, so good. And because probably DSTL is in the room, it's going really well. So yeah, but it's risky, and but it does provide a big uplift in what you can do if you can start observing satellites during the day. And most LEO satellites you can see with a signal to noise of 200 sometimes. And that really makes a difference. So we're happy to take the risk and mitigate as much as we can.
All right, thank you. Do we have any questions online? No? Good. So what's your sensitivity level? I mean, of small object can you detect?
So in LEO, we can see down to 5 centimeters. In GEO, we regularly see about 16 UU CubeSats. So that's about roughly about it, yeah.
Okay, thank you, impressive. Okay, let's thank our speaker again.
Thank you.